Hello. Finally, we have problems 17, 18, 19. So this is pretty similar to the last set of problems. The only difference being that there's an inductor. So we use our rules and we know that inductors act as shorts in steady state, right? So we know that this circuit has been around for a long time. Initially, the switch is in position 2 for a long time. So we're just going to redraw this circuit to look like that. So the inductor is in steady state because it's a long time, and switch is in position 2. So let's redraw that. We'll have our switch here, and then the inductor acts as a wire like that. And here is IO. So if this was sitting for a long time, it has no connection to the battery. If you look at this red part right here, you see that it's not connected to the battery. So the initial current can't be anything but 0. Next step, we're going to redraw the circuit in position 1. And then we're going to find REQ for the inductor. We're going to find the time constant for the inductor. And finally, we're going to find the final current that the inductor will be at after it reaches steady state. So let's redraw the circuit. So we'll start with our source over here, 40, the 6K. And here's the 10K. And then here is our position 1 connection. There's the 7K. And there's the inductor. Now this 2K right here, you could draw it, but since it doesn't connect anything, it's not particularly useful. So we're just gonna get rid of that. All right, so the first step is we're gonna find REQ. And to do that, we're gonna use our Thevenin steps, and we're gonna remove the reference point from the circuit and replace it with an open. And then we'll remove any sources and we'll replace them. Now this is a voltage source, so we'll replace this one with a short. And now we have to find R Thevenin or REQ. R Thevenin equals REQ. And from this perspective, we've got a 7K, and then it splits off into a parallel 6K and 10K. So that means that we have 7K plus 1/10 plus 1/6. And these are killi. That's -1. And we're going to get 10.75 kiloohms. All right. Now, we will next find the time constant. Time constant tau for inductive circuits is on your equation sheet, right? You can find it in the DC section. And that is going to be L/R. Value of L in this was 3 milli. And the value of R we just found was 10.75 killi. So when you put those together, you're going to end up with a pretty small time constant of 279 nanoseconds. Finally, we're going to be looking for the final current. Okay, so again, we assume steady state conditions. All right. So we go back to our drawing. All right, let's put the source back. And let's replace this inductor with its steady state counterpart. All right, so inductors. So here's a 7. and inductors are shorts. So they look like that. Here's your battery. And now all you do is find IL, which is gonna be I final. IL in this case is pretty easy to find. All we have to do is use what we know about Ohm's law and parallel circuits to find the answer. This is like a pretty normal problem. You can use nodal analysis if you want. It's probably not necessary and you might make a mistake. So I would probably suggest solving this problem the same way you normally would. So you might want to do something like this where you find the total resistance. And that's 10.1. And then you would use that to find total current, IT. And that's going to be 40 over 10.1. Sorry about that. So that's around 3.95. And then once you have that, it's pretty trivial to find the rest, right? Just a current divider rule. So we've got I final equals 3.95 over, and there's the branch resistance, which is 1 over 10 plus 1 over 7 to the negative 1. And then that's over 7, which is the resistance of the branch. And that's going to give you 2.33. That's in milliamps. That's I final. So the last part is you're just gonna plug it into the general equation again. Remember, use the general equation. Do not use the quick equations. So that's I final plus I initial plus I final e to the negative t over tau L. And then we'll just plug all the numbers in. So I final is 2.33 plus I initial, which is 0, plus 2.33, or sorry, minus. E to the negative t over 279 nanoseconds. And there you go. Just written out a little neater. 2.33 minus 2.33 e to the negative t over 279 nanoseconds. And if you plot that, so if you notice, this is going from a smaller value to a larger value, right? Because it starts at 0 and it goes to 2.33. So this is an exponential increase. That means we want the curve to look something like that, right? But we do have to define those same values again. We have to define I final, 2.33, I initial, which is 0, and that's on the amp side. And then we have to define our endpoint. Now our endpoint's always 5 tau. Tau being 279 nanoseconds times 5 is going to get you 1.3 0.95 microseconds, and that's the unit we'll put t in. So that's 1.395, and then all we have to do is kind of make a curved line like that. It kind of approaches asymptotically to the I final, and we consider that part right there to be steady state, and that is problem 19.